Okay. Well, before I get started, I want to show you one picture taken 30 years ago. So can you tell where Carl is? Right, so this is Carl Heiles, and this is Bill Rich, and this is me. So this rafting class was an essential class for Carl's student. And now it's one of my delightful memories of the graduate school. And of course, there are so many memories on Jack Daniel and Puerto Rican rum. So, well, thank you very much for everything for Carl. And congratulations on your retirement. Okay, I'll be talking about missing supernova remnants and so-called H1 forbidden velocity rings. In the galaxy, in the Milky Way, there are about 300 supernova remnants known. And this number is much less than what we would expect from the supernova rate and their lifetime, at least an order of magnitude. And so most supernova remnants are missing. Well, there are both astrophysical and observational reasons. And first, most supernovae are co-collapse supernovae, so that they might produce superbubbles and supershells instead of isolated supernova remnants. And secondly, interstellar space is largely filled with hot ionized medium, where the density is too low for supernova remnants to become visible. And observationally, is the background contamination. Radio supernova remnants are usually identified in radio continuum. And in radio continuum, so all the supernova remnants are faint, and they are easily confused by this strong background emission. But for all the supernova remnants, there's another tool, namely H1 21 centimeter line. Well, this graph plus momentum as a function of radius of supernova remnant. So this is where supernova becomes radiative, and these radiative supernova remnants do have rapidly expanding atomic shell, which may be visible in H1 21 centimeter line. So we may call them H1 supernova remnants. But in real world, there are foreground and background emission. So what we usually see is limited to this cap portion at highest positive or highest negative velocities. Once detected, this H1 shell provides direct information on supernova remnants, such as momentum and kinetic energy, so which are quite important parameters for supernova remnants. So one project that I did with Carl was to search for such fast expanding H1 shells associated with supernova remnants using this Heckrich 85-foot telescope. And as many of you know, this telescope was destroyed in a windstorm in 1993. And the picture that you see is the one taken just after the collapse. Okay, anyway, so we observed 100 supernova remnants visible at Heckrich and detected about 15 H1 supernova remnants. And we did a similar survey toward the southern supernova remnants with Jihyun and Naomi, and also detected about 10 supernova remnants. So in total, there are about 25 supernova remnants. And they are candidates in the sense that we need to map those supernova remnants to confirm that they are really H1 supernova or associated with supernova remnants. So 25 is very small when we consider that there are more than 2,000 supernova remnants. So we come to the question, where are all the H1 supernova remnants? Well, in order to address the question, it is helpful to look at this large-scale LV diagram. Here, the y-axis is the galactic longitude from 0 to 90 degrees. And as we can guess from their line profiles, H1 supernova remnants appear as small bumps. just beyond this galactic background emission. And now we note that there are bumps which looks very similar to H1 supernova remnants in this large-scale diagram. Like this one, or like this one, this one. So we call them forbidden velocity wings and propose that they could be those missing old supernova remnants. And we did some follow-up studies and found one very nice example, namely FVW190. And it turned out this is an expanding shell, expanding at 80 kilometers per second. And it is not visible in radio continuum. And its physical parameters and also radio surface brightness limit are consistent with supernova origin. So some forbidden velocity wings indeed might be old supernova remnants, visible only perhaps in H1 21 centimeter line. Well, now we can do a more systematic study using the GALFA data. And Josh already presented everything about GALFA data. I just want to mention that I-GALFA survey is a survey of the inner galaxy available at RSCBO, which covers galactic longitude from 30 to about 80 degrees and galactic latitude plus minus 15. So how does forbidden velocity wings look like in I-GALFA data? Well, if we apply a medium filter, we can look at them more clearly. And well, depending on the criterion, there are more than a few hundred forbidden velocity wings. Well, this, by the way, this is a slice in galactic latitude plus minus, I think 1.5, and there are more slices. So in total, there may be about a few hundred forbidden velocity wings. And we found that 4 known supernova remnants appear in this map, like W44, W51, and G54.1, and they correspond to these forbidden velocity rings. And it is again 10% of the known supernova remnants in this survey area. I think I can skip this slide. I just want to say that we can compare the momentum of these H1 supernova remnants to theoretical results. And according to our preliminary result, they seem to be consistent with each other within the uncertainty of the initial explosion energy. Okay, how about forbidden velocity wings without supernova remnant counterpart, which most of the forbidden velocity wings do not have the counterparts? Well, they seem to have very different shapes. Well, I'm showing some examples where some looks like shells, possibly expanding shells, but some appears very unique, appears to have very unique morphology, like this one. So it seems that the nature and the origin of these forbidden velocity wings are rather diverse. I want to mention that the forbidden velocity wings, or these shell-like objects at negative velocities, they might be on the far side of the galactic plane, so the distance is very large, so they might be supershells rather than single supernova remnants. And this one is particularly interesting. So I want to focus on this particular object in the rest of my talk. So this one, FVW40, appears to be a complete ring with a complicated structure inside. In a sense, it looks like a cartwheel, or perhaps crushed cartwheel with hub and spokes. And the estimated distance is 20 kiloparsec, which means the size is almost a kiloparsec. And if it had been produced by multiple supernovae, it requires more than 70 supernova explosions. So it is certainly a supershell, but it is about 400 parsec below the galactic plane. So the supernova origin is not unlikely. Instead, there is a high velocity cloud here. So as you can see in this image and in this position velocity diagram, the alignment of this high velocity cloud with this supershell is quite striking. And this high velocity cloud, compact high velocity cloud, has been known to have this head-tail morphology from previous studies. And our RSVH1 image shows that it has blunt cone shape with steep boundary and also flaring faint envelope. If it is at a distance of 20 kiloparsec, at the same distance as the supershell, then its size is about few hundred parsec, and the line width is very large. Well, this high-velocity cloud, compact high-velocity cloud, belongs to the so-called high-velocity cloud complex, GCN, or galactic center negative. Well, this is the galactic plane, and this is where HVC 40 is located. And this is a collection of very small clouds distributed over a very large area. And the distance estimated range from 15 kiloparsec in the galactic plane and about 35 kiloparsec at galactic latitude minus 60. And it has been pointed out this whole complex appears to be composed of several subpopulations with different origins, possibly at slightly different distances. So the bottom line is that 20 kiloparsec for this compact high-velocity cloud of 40 or 40 is not unreasonable. So based on the location of supershell and also the location of this compact high-velocity cloud, and also based on their comparable distances, and this supershell is very likely to be formed by the impact of the compact high-velocity cloud. But it is not clear how the collision has produced the morphology that we see, that we observe now. Namely, what's the relation between the compact high-velocity cloud and the hub, and what's the origin of the hub and spokes? Perhaps if the diffuse interstellar gas is confined to sheaths and filaments, then perhaps we may have this kind of morphology. So this needs to be explored in future studies. Well, I think I can summarize my talk. Well, most of the supernova remnants are missing, and forbidden velocity wings are candidates for missing all the supernova remnants. And there are indeed forbidden velocity wings with characteristics consistent with supernova origin. But the I-GALFA data image suggests that the nature and the origin of forbidden velocity wings are diverse. And in one case, FVW 40, for example, is very likely a supershell formed by the impact of a compact high-velocity cloud. And this system shows that some compact high-velocity cloud can survive their trip through the galactic halo and can inject momentum and energy to a galaxy. Well, there was a talk about Smith cloud today. And the mass of Smith cloud was 5 times 10 to the 6 solar mass, whereas the mass of this compact cloud is like 5,000 solar mass. So there is a huge difference between Smith cloud and this compact cloud. But this could be another example for high-velocity cloud interacting with a galactic disk. Thank you very much for your attention.
Thanks a lot, Bon-Chul. Questions?
Thank you. This is really interesting. Do you have any predictions for observational characteristics that would distinguish the two modes of creating supershells? Either it's supernova or potentially HVC colliding. Would it be some distinction in the velocity dispersions and the morphologies? What would your opinion be?
Well, in this case, we were able to say that it is due to high-velocity cloud collision, because we can see high-velocity cloud at the center of the supershell. But if we don't see high-velocity cloud, then I think it will be difficult. But perhaps if we see some radio continuum, faint radio continuum, then we may be able to say
there might be some other tracers. Yeah.
your compact high-velocity cloud sounds very interesting. Is there any information about the metricity or any other properties of the cloud?
So here are some physical parameters of compact high-velocity cloud. The size, mass, and kinetic energy. One thing you may notice that its kinetic energy is much less than the initial energy that we estimated for supershell, and it implies that the mass of the high-velocity cloud, if the supershell was produced by the collision of this high-velocity cloud, then it implies that the mass of the high-velocity cloud, original mass, should be much greater than the mass that we observe now.
Thanks a lot, Bon-Chul.
Okay.
And before we break for coffee, Don would like to make a comment. Very brief comment.
I wanted to withdraw my complaint about the bending of the sheets. I'll tell you why, as Isabel pointed out my error. This is my walking stick. It breaks into 3 parts, but imagine they're made out of rubber. If I try to bend them in this direction, if I try to bend them along the sticks, they're going to resist and flip back. Whereas if you want to bend them this direction, you don't have any problem at all. So you're going to, the way that the thing could be most easily disturbed is to have the filaments end up forming, or the cusps where that look like filaments along the line of the magnetic field. I hope I said that well. And I apologize for complaining.
Thanks, Don.